Welcome to Power Machines N5. Today's presentation is on calorimeters. Calorimeters is part of your module 3. And so what I will advise you to do before I begin is that you go and watch my video on enthalpy and steam. You will find that video in the Power Machines N5 playlist. Watch that video and then come and watch the video on calorimeters. The reason is because if you do not understand enthalpy, then understanding calorimeters will be very difficult for you. So begin by watching the video on enthalpy and steam, and then come to watch the video on calorimeters. So for module 3, I have 3 videos on this platform that you need to watch. The first one is enthalpy and steam. The second one is calorimeters. And then finally, there is the video on steam plants. So you need to watch those 3 videos because they are all part of module number 3 in your syllabus. Having said that, let's begin. So now, as an introduction, I just want to tell you what calorimeters are used for. Okay, so basically, calorimeters are devices that are used to measure the quality of the steam. And so for Power Machines N5, we will look at how calorimeters are used to find the dryness fraction of the steam. And so there are 4 types of calorimeters that you need to be aware of. The first one is what we refer to as the barrel calorimeter. Okay, barrel calorimeter. And this calorimeter uses the fact that the heat that is lost from the steam is gained by the water and the calorimeter. And so when we put that equality into place, we can then solve for the dryness fraction as follows, okay? So this expression here represents the heat that is lost by the steam, and that is equal to the heat that is gained by the water plus the heat that is gained by the calorimeter, okay? And so if you put that equality like that, you can then solve for x, and that will give you your dryness fraction. That is how we find the dryness fraction using the barrel calorimeter. However, this calorimeter is not very accurate in determining the dryness fraction. Another calorimeter that is used is the separating calorimeter. And in order to find the dryness fraction using a separating calorimeter, we divide the mass of the steam, the condensed steam, by the total mass, which is made of the mass of the water and the mass of the steam. Okay, so as you can see in this equation, for finding the dryness fraction when we're dealing with a separating calorimeter, we take the mass of the steam, the condensed steam, and we divide it by the total mass. And the total mass is made of the mass of the water plus the mass of the steam, okay? And so if you use that equation, that allows you to find the dryness fraction of the separating calorimeter. And usually this dryness fraction, we refer to it as x1, okay? So you will usually find that it's going to be written x1 is equal to ms over mw plus ms, okay? And this here is x1. And so after the separating calorimeter, we have the throttling calorimeter. And basically in power machines, when you come across the expression throttling, okay, if they tell you that throttling is taking place, that simply means that the enthalpy before is going to be equal to the enthalpy after. Okay, that is the case when you're dealing with throttling. If there is throttling, then the enthalpy before throttling is equal to the enthalpy after throttling. So now when you're dealing with a throttling calorimeter, The enthalpy that you have before is wet, okay? The enthalpy of wet steam, because the steam is wet before the throttling calorimeter, and then it is superheated after the throttling calorimeter. And so that is why we say that the enthalpy of the wet steam before the throttling calorimeter is equal to the enthalpy of superheated vapor after the throttling calorimeter, because enthalpy before throttling is equal to enthalpy after throttling. And now from this equality here, if we now write HW equation and make it equal to HSU equation, then what we will get is this. And from this here, you can see that we have X, which is the dryness fraction. Then you can rearrange this equation to find X. And if you do that, what you will get is this, okay? And now it's really important for you to understand at this stage here that the pressure at which the steam is before the throttling calorimeter is not the same pressure at which the steam will be after the throttling calorimeter. And so therefore the value of HF and HFG that you read here, you will read them at a certain pressure. And then the value of Hg that you read on the other side of the equal sign, you will read it at a different pressure, because the pressure before throttling is not equal to the pressure after throttling. So this Hg, you read it at a different pressure, and HF and HFG, you will read them at the pressure before throttling. Hg, you read at the pressure after throttling from the steam tables, okay? You read Hg from the steam tables, but you will read it at the pressure that you have after throttling. And HF and HFG, this is before throttling. This is the enthalpy before throttling. So you will read these values at the pressure before throttling, okay? It's very important for you to understand that. Do not make the mistake of reading HF, HFG, and HG here at the same pressure, okay? These are not at the same pressure. HF and HFG are at the same pressure, which is the pressure before throttling, but Hg here is at the pressure after throttling, okay? So you read them accordingly, okay, when you are reading values from your steam tables. Very important. And so with throttling, just remember that enthalpy before is equal to enthalpy after, and the state of the steam before throttling is wet. The state of the steam after throttling is superheated. Therefore, you will have the enthalpy of wet steam before the throttler will be equal to the enthalpy of superheated steam after throttling, okay? Very, very important. And from this, then you write the expressions of these enthalpies, the equations for them, and from there you solve for X. Remember that HF and HFG, you read them at the pressure before throttling, and Hg, you read at the pressure after throttling, okay? Very important. So after the throttling calorimeter, what we have is that before we move on, I need to tell you this, that the dryness fraction that we get for the throttling calorimeter is referred to as X2, okay? So do not get these mixed up, okay? X1 is the dryness fraction that you get from the separating calorimeter, and X2, which is given by this expression here, is the dryness fraction that you get for the throttling calorimeter, okay? Very important, always remember that. And so after the throttling calorimeter, as I was saying, we have now the combined separating and throttling calorimeter. Why is it that we combine the two? Is because either one of them is not very accurate. So all these calorimeters that we've seen so far are not very accurate. But it turns out that if you combine the separating calorimeter with a throttling calorimeter, then the result that you get is more accurate. Okay, so usually that is what we're trying to achieve, is find the dryness fraction of the separating calorimeter and then that of the throttling calorimeter, and then combine them to get an accurate value for the dryness fraction. And so to get the dryness fraction of a combined separating and throttling calorimeter, all you need to do is to multiply the two dryness fractions. And so that is now x, okay? This x is actually the dryness fraction of the combined separating and throttling calorimeter. And the way we find this x is by multiplying x1, which is the dryness fraction of the separating calorimeter, and x2, which is the dryness fraction of the throttling calorimeter. And so when you combine them like that, then you get a more accurate answer for the dryness fraction. I need to say here that when we combine them, we multiply the dryness fractions, okay? It is not a sum. I cannot tell you how many times I've seen students adding these two, okay? It is not a sum, it is a multiplication. So to combine the two, you need to multiply the dryness fractions.